A pygmy shrew races through life at 835 heartbeats a minute and dies in about 2 years. An African elephant sustains a slow, steady pulse of 28 beats per minute and survives for 7 decades. When you calculate the total count of heartbeats over their entire lives, the difference in years disappears. Despite their vast difference in scale, both animals accumulate approximately 1 billion cardiac cycles before they reach their thermodynamic limit. This 1 billion beat threshold acts as a universal baseline for almost the entire mammalian kingdom. It suggests that organisms don't age by the rotation of the sun, but by biological proper time, an internal clock that measures life in physiological cycles rather than calendar years. For most creatures, lifespan isn't a chronological timer. It's a fixed biological budget. Curious, if we apply that same math to ourselves, our resting rate of 70 beats per minute should exhaust our biological budget by our late 20s. Yet human data reveals a massive deviation. A healthy person living to 80 will experience between 2.5 and 3 billion heartbeats, nearly tripling the limit seen in almost every other mammal. We aren't the only outliers. Bats, birds, and whales also push far beyond the 1 billion beat ceiling, enduring significantly longer than their metabolic rates would predict. These species are bypassing a standard law of nature, pointing to a specific biological strategy that allows them to decouple physiological wear from chronological time. To understand how they do it, we have to look past anatomy and into the second law of thermodynamics. Every heartbeat produces heat, friction, and cellular damage. Physicists call this microscopic wear entropy. The 1 billion beat limit isn't about muscle fatigue. It's a cap on total entropy. To live longer, organisms must reduce the entropy produced by each individual heartbeat. If you make each beat thermodynamically cheaper, you can fit more of them into the same lifetime budget. Some species achieve this through time dilation, stretching their budget by slowing the clock. The bowhead whale uses intense diving bradycardia, dropping its heart rate to a few beats per minute to suspend metabolic consumption during long dives. Bats use a similar suspension through thermal torpor. By lowering their body temperature during hibernation, they reduce the thermodynamic cost of staying alive during the harshest months of the year. These animals don't necessarily have a bigger budget. They simply spend their fixed allowance over a much longer period of time. Humans, however, use a different strategy. We don't hibernate or dive. We stay active and warm year-round. Our advantage comes from how we distribute energy. Our brain consumes a massive share of our resting energy for high-precision biological control. This neural investment precisely regulates the body, reducing chaotic metabolic noise in other organs. With less internal friction, the entropy cost of every heartbeat physically shrinks. In a very literal sense, our intelligence increases the thermodynamic efficiency of our bodies, buying us 2 billion extra beats of biological time. If every beat adds to a finite budget of wear and tear, then shouldn't we sit as still as possible to save them? Recent studies on elite athletes suggest the opposite is true. While exercise temporarily spikes the heart rate, it forces a long-term change in the heart's efficiency. In this 24-hour comparison, an athlete's workout temporarily spikes their heart rate, forcing cardiovascular adaptation. Afterwards, their resting rate drops significantly below a sedentary baseline. Calculating the total area reveals that physically fit individuals spend about 10% fewer heartbeats every single day. Exercise is an investment. You spend a few thousand beats to save tens of thousands later. For humans, cardiovascular training is our active version of the whale's dive. It is how we manipulate our internal clock. While we cannot change the laws of physics, we can change the rate at which we consume our allowance. We age by the biological beat, not the chronological year. Improving cardiovascular efficiency is the best way to manage our finite budget of biological time.